property. That is the IBM property I'm going to talk about. That's what historically Professor Abdasmani told us the origins of the Leavitt path algebra. I'm just going to go through that quickly just to remind you. Better? This is good? Okay, so I'll go back to the origins of Leavitt path algebras, the motivation and why the name comes with it. Just again, going through it. And then I'm going to talk about how to calculate the IBM property of various algebras. Now, the motivation is again any real number, if you have m copies of R, isomorphic to m copies of R, that's going to be isomorphic. As long as n and m are exactly the same, and we can replace R with any field or any division ring that we know from the vector space basis. Can we replace this with any ring? So the question becomes, as a right R module, say, can I have R copy, n copies of R, isomorphic to m copies of R as right R modules? And this is only true if and only if n and m are equal. So do I have this property? The answer is yes, if R is a commutative ring or a Noetherian ring. And we have seen some examples in Professor Anderson's lecture yesterday. But the answer is no if you take an countable infinite dimensional vector space V and the endomorphism ring over it as your R. R is a free module with basis 1, but at the same time you can construct another basis of cardinality 2. So that says R is isomorphic to 2 copies of it. So the answer turns out to be yes or no, depending. Now, here comes the definition of the invariant number. If the answer of the question I asked is positive, then that ring is said to have an invariant basis number property. So any commutative ring or a Noetherian ring has IBM as the abbreviation for the invariant basis number. However, as we see, the second example tells me it is a non-IBM. So we say R is either an IBM ring in this case or a non-IBM ring. With the non-IBMness, we associate it with a type, meaning that recall that R was isomorphic to 2 copies of R, so I say R is a non-IBM ring of type 1, 2. To make this definition more clear, I'll give you the definition. This was the first question. This was the question that Leavitt asked in the 60s. For any given positive integers m less than n, can we find a ring having a free module with a basis of m elements and another basis with n elements, but no basis with k elements if k is not equal to m but strictly less than m. And that's what we call a ring of type non-IBM, a ring. That's what we call a ring, a non-IBM ring of type n and n. So m is the smaller letter, integer, and n is the bigger. And Leavitt answered this positively, saying that yes, there exists, and he actually constructed those algebras. And today we call them the Leavitt algebras of type Mn. If for every m less than n, and field to be K, we can find a ring such that M copies of R is isomorphic to N copies. However, no K copies of it is isomorphic to M if K is not equal to M plus K plus M. So, the algebras that he has constructed nowadays are called Leavitt algebras. They are of type Mn. Now, let me go back. The easy part, of course, is to find an isomorphism between M copies of R and N copies of R. If you construct an isomorphism, then it's easy enough. The hard part is to show that the second part, that show that this guy is not going to be isomorphic to M copies of R for any K less than M, not equal to M. And that requires the tool that, again, is introduced today, the monoid of a ring. I have exactly the same scheme, but it doesn't hurt to go through that. For any ring R, P is a finitely generated projective right R module in case you have another right R module Q, such that P direct sum Q is as some integer copies of R. And then we take the isomorphism classes of each finitely generated projective R module. I denote the isomorphism classes by the bracket. So P bracket is the isomorphism classes of finitely generated E module, projective right R module P. And we basically have the direct sum of P and Q. So as our addition, so this operation makes D of R a monoid. If you consider R, recall R is a free module over itself, so it's projective, it's finitely generated, it has only one copy. So if the isomorphism class of R is a typical element in D of R. So if I consider the cyclic submonoid generated by this element, I will denote that by U of R. I use monoid and semigroup interchangeably, so sometimes it's more convenient not to. It's more convenient to get rid of the zero module out of my monoid, so I use B star of R for the semigroup, and the associated semigroup for U is going to be by U star of R. Now, this monoid, the cyclic submonoid generated by R, the semigroup, is important in our case. In the previous talk, recall that we had seen the monoid constructed for the Leavitt algebras of type 1n. I'll get back to this. Now, another notation I need is the Grothendieck group. Just wanted to go briefly over it for the ones who bear with me, for the ones who are familiar. For an arbitrary non-empty commutative semigroup S, what we do is we define an equivalence relation on S cross S with the ordered pairs, such that these are equivalent if there exists an X in S, such that ADX is equal to BCX. So via the equivalence relation, we look at the equivalence classes. We call G of S the set of equivalence classes, and we make it a group via the multiplication defined in this manner. And this guy is the identity of this multiplication, and the equivalence class of BA is the inverse of the equivalence class of AD. G of S, the set, becomes an abelian group that satisfies the following if you fix an x and basically define a function phi of x from S to G of S in the following manner, you map A to AX cross X, the equivalence class of this tuple, then phi x is a semigroup homomorphism. And if you take any x and y, we realize that phi x and phi y are exactly the same. So phi is basically defined independent of the choice of x, so I can omit that subscript. So the for the any semigroup S, GS is called the grotesque group of the semigroup S, GS, together with the semigroup homomorphism phi from S to GS that satisfies the following relation for any abelian group H that you pick, and for any semigroup homomorphism from F from S to H. Then you can basically factor through via the homomorphism G of S, right? So G of S together with the phi is basically for any F and H that you pick, there exists such that this diagram. So that's the definition of the grotesque group. This is exactly the, this is exactly how we basically embed, if you take the natural numbers and the grotesque group of the natural numbers is the integers. How we basically construct Z out of that is exactly the same. So this is the general. Now, this is a special name. If you take an arbitrary ring, V of R, the monoid that we have defined, the grotesque group of that semigroup, is, well, you can put a star here if you like, is basically called the grotesque group of V of R, which is denoted, the grotesque group of V of R, which is called the K0 of the ring. Okay? That goes into the relative K groups. There are different K groups. This is the 0 to K group of any ring. So for an arbitrary ring, you start calculating the K groups, which are some invariants for an arbitrary ring, which is also important in the classification of the isomorphism problems that we deal with. I'll note this, but this will pop up again. For arbitrary semigroups, S and T, even if you have S to T, a function, a semigroup homomorphism, which is one-to-one, does not necessarily imply that their corresponding grotesque groups are embedded in one another. So one-to-oneness is not preserved under this extension of the functions into their grotesque groups. However, this is a nice property that we have. For an arbitrary ring, if I start with an arbitrary ring, consider the cyclic monoid generated by R. It is clearly an embedding because it's a submonoid of V of R. Okay? And also for this end, if I take the induced map into the grotesque group of G of R and to the grotesque group of V of R, which is the K0 of R, this map is injected. Okay, that's a nice observation because we see the grotesque group of V of R is embedded in the K0 of R. This will be useful in our calculation. Now, the Arginian property of the ring is detected by the K0 tensor Q. Let me put the notation here. If I consider the set to be V of R, then the grotesque group of that is the K0 of R. Then I tensor it on Z with Q, so I get this set. The element that is over here is this is the isomorphism class of the projective module P. I denote its image because this basically is embedded in the K0, I'm going to denote it by via some C. This is in a monoid, in a semigroup. However, now this is in a group. So I visualize P in the group here via this notation. And when I tensor that with, with 1, I call this as P sub. Now, if R has IBM, this is a well-known theorem. If R has IBM, then the cyclic monoid generated by R has to be infinite. Recall what the IBM property is. If I consider well, this was one notation that I had used, I from 1 to n. Okay? I can basically use the notation as additive notation. R is the equal in V of R. Okay. If R has IBM, that means any copy of R. Oh, okay. Give me 1 second. Let me write it in this way. This, I will write this as in the additive notation. M copies of R, I'm adding R projected modules, is exactly N of R. So I'm basically passing to this notation now because I'm in the over here. Okay? This is an element because you're basically taking R, 2, R, 3, R, etc. The set that you have here. If this set is, if at some point 2R, 3R, say this is your U of R, okay? The cyclic submonoid is generated by R. So at some point, say this guy is equal to n plus 1 copies of R. This is what happened in the Leavitt algebra 1n case. So this says 1 is isomorphic to n plus 1. What this makes is this set is going to be a finite set. So at some point it goes back. Well, maybe not necessarily 1 here, but you might get another copy of it. So, however, that tells me that this is not going to be an IBM. However, if it's IBM, that means any copy of R is not going to be isomorphic to R. That means U of R will be an infinite set. You have R, R, 2R, 3R, and then moving on further. It's not going to repeat itself. It's not going to be equal to another element in the set again. Okay? So these are equal. Well, this is if this is non-zero in here, then basically it tells me when this is going to be as well. So I can now leave it on this. Leave this information on the side. We go to the commutative semigroups generated by a finite set of generators. Those are called the finite representative commutative semigroups. I want to show you a nice tool that's going to be helpful. If you have the generator set gamma, a finite set, and say these are your relations. Okay? It's a semigroup, so you take any n coefficients of gamma. But for the sake of simplicity, I don't want zero in there, so I just got rid of the zero. So I want to keep it as a zero. The relations are xi is equal to yi. Recall that you're in a semigroup, so I have to relate my relations as these equations. I want to define a geometric representation of the semigroup with respect to any generator and relation. This is what we do. We construct a graph with the vertex set and omega minus 0. And the edge set is going to be coming from the relations. What I do is I look at the relations xi equals yi. Well, then xi is a point in this vertex set. And yi is another point in this vertex set. I join the xi with the yi via the edge wi. Those are going to be the edges. And then after I put one edge for each relation, one wi for each relation, I'm going to take all possible translates of it by the elements in the grid. Then the connected components of the graphs are going to be the elements in this. Let me give you an example. Okay. So that will be the geometric representation of the semigroup. For the quadratic group, now instead of n omega, I'm going to extend the whole picture to z omega via the translates in the z omega then. That will give me the quadratic. Let me give you an example to be more concrete. Say you have a semigroup generated by the two generators V and W. So I took two, to be able to represent it nice, I'm only taking two generators, so we have a two-dimensional board here. V is the first axis, W is the second axis. And I took the relations V equals 2W, V equals 5W. Okay, so now, the geometric representation. Now the semigroup generated by this and these relations is, look at the black dots, the grid that you have, the N grid that you see here. The point 1, 0 represents W. This is 2W, 2, 0. 3 is a W, 4W, etc. And the y-axis is, this is omega, 2 omega, 3 omega, 4 omega. This point right here is the point 2, 2. So it is 2B plus 2W. So that's how I represent all the elements in n omega minus. Well, I don't want to include 0, so I took that out. All the black dots that you see are elements in n omega minus 0. Now, I look at the relation. The relation says 1 is equal to 2W. That means 1 is here, 1, 0, is 2W. 2W is this point. So the blue line that I have here is the first relation. That's the edge that I put. The second relation, is that clear? The second relation says B is equal to 5W. So B is the third, the edge, the vertex of the second edge. That's again 1, 0, this is B. And 5W is right here. So I put this dark red second edge. That's my second edge. What I do is I translate this blue line on the whole grid via n. So I can go only to the right and to the top. Okay? And I have, so what I'm doing is I'm connecting every line segment parallel. And I do the same thing with the red line, so you see the red translates again on the grid. This is the geometric representation of the semigroup generated by those two vertices and these relations. Okay. Another one. Take this one. V and W. And the relation is V equals V plus W. Trust me, these are very familiar semigroups. It will pop up soon. I look at the representation. So again, I have the grid elements, all n omega minus 0 elements, all the black dots here. And now the relation, I have only one relation. V is this point. V plus W is the point 1, 1. And that's the line that I have for for the geometric representation, the edge, and then translate this. So this goes, etc. Okay. Now, it's easier to explain here, so let me say. The semi-group that you have actually here is, I can tell you that this whole line, this is a pan-connected component that you see geometrically, right? B is equal to B plus W, but that is equal to B plus 2W. Well, replace this B with another B plus W, so that's B plus 2W. Well, replace the same B with another B plus W, so you get B plus 3W. So all these are exactly the same, so they are they are exactly the same elements. So the path components are showing me different elements here. What is the semigroup? Let's compute the semigroup for this one. That is going to be the set, the semigroup S is the equivalence class of 1, 0, equivalence class of 2, 0, equivalence class of 3, 0, etc. and 0. And union. Is that it? Well, how about W? I have, in the equivalence class, I have only one element. This is not connected to anything, but it's an element of the semigroup. So is this, so is this, so is that. So that's going to be the semigroup that you have. Okay? S is basically the union of those two sets. Okay? If I want to do the rotary group, then I basically extend this relation here onto Z omega. Now, so you extend it everywhere. Now we're happy because what happened is I was able to take it to the left. Taking it to the left means subtracting. The reason I cannot go to the left here is because you're only allowed to add. So you can go only to the right and to the top. You're in the semigroup. Once you get to the rectangle group, now we have the inverses, additive inverses, so I can do the left operation. So now you see that this is nothing but every integer is equivalence class. The rectangle group of S is basically isomorphic. Okay, so it's easy to visualize it. Questions? Okay, this was just arbitrary semigroups that we constructed on generators. Now we go to the semigroups. Again, Professor Anderson mentioned this in the morning. I'll pass this. This is the definition of the graph, a single source with a regular vertex. We're all familiar with now. We are defining on a graph semigroup. I'm using the notation a little here to be what Professor Abdeswani mentioned in the morning as A sub B. I am denoting with by abuse of notation. So I'm saying it is not it is generated by the vertices. It's a semigroup generated by the vertices and via the relations on the regular vertices. The regular vertices mean they are not 6, they only generate finite remaining edges. And these are the relations. So for every vertex, B is going to be equal to the sum of the targets, the ranges of the edges that it emits. So that's the relation. And we embed the if I represent the embedding of this semigroup into its quadratic group as phi, now the relations will become, instead of equality, now I can use it as the subtraction, the negative. And I sometimes denote this as 0, so that the quadratic group is. Okay, now, this was the familiar notation, the complex algebra. Consider the directed graph E with one loop at B and another edge to W. You have two vertices, B and W are the generators. Here we have B and W. It is exactly the same graph that we had a couple minutes ago. The relation I have is, you look at, W is the same, so there is no relation there. B is a regular vertex. B emits an edge to itself, and it emits another edge into W. So the relation is B is equal to B plus W. So that is the semigroup of this graph. It is exactly right here. And the quadratic group is this. Okay, Leavitt path algebras. Let's pass this. We have the definition. Now, in general, it is hard to find a monoid of arbitrary ring. However, if R is a Leavitt path algebra, again, in the morning we have Professor Agnes mentioned it, so I'm going to recall it again. I'm not going to give the proof of this theorem. This is a nice connection. The graph semigroup and the monoid of the Leavitt path algebra are isomorphic. It is based on a nice theorem of Bergman. And the important thing here is that the sum of the vertices in the semigroup is mapped to the free monoid L itself. That's another crucial thing. Now, Professor Abeyabasu will be giving us either in this content the proof next week. So you will see this theorem again. Okay? And Professor Pereira might be using this in a more general setting. The theorem also holds for separated Leavitt path algebras. So they might be even the whole Leavitt, as we have seen in the morning. It is also valid for more generalized Leavitt path algebras. You can whole Leavitt path algebras, Leavitt cone path algebras, whole Leavitt path algebras on the separated graphs. The similar result holds, which actually helps us to be able to calculate the IBM type of it. This is a very complicated thing. Okay. So, after looking at this, we have B into L. The type, if the Leavitt path algebra has type 1M for some natural 1M, then we see that one copy of L is equal to M copy of L, where M is the minimum natural number satisfying this property. Okay. Moreover, if you look at the order of this element, order meaning, well, recall that this element is in U of R, or we have L for now. However, this is embedded in the quadratic group. And because this is one-to-one, recall we mentioned that the quadratic group of this guy is one-to-one as well into here. So this is an element in the quadratic group of U or L, which is also so if I trace the diagram, basically, this is one-to-one, it's an injection. So this guy is also living in K0R. So the order is, if the order of this is M here, and move along, then it is exactly, well, the order of L in K0 of L is going to be M minus 1 because this is going to give you the identity if you have M minus 1. And these are okay, so this guy is another invariant that we have, so I'll keep this in mind. This is called the unit order of K0 of LK. K0 of LK is an important invariant for the path algebra, so is this number here. But again, the type basically tells you where this sits in your K0. So if you know the type, that's good. That's going to be enough. Okay, this theorem, this is a very IBM theorem, tells us a criteria when the Leavitt path algebra is IBM and how to compute this basically. Now the theorem is general the theorem is valid in a more general setting, but I just wanted to mention the Leavitt path algebra. The first result came with the cone path algebras are all IBM actually. Then this generalization occurred. It's valid for arbitrary cone Leavitt way. So anyhow, it says L is IBM if and only if the sum of the vertices, recall the sum of the vertices is resembling your L in the K0. This is not the Q span of the relations V minus. So this is the relations that generated semigroup of the graph. Going back to this example, the relation that we have here for this example is V plus Vn. Well, what is the element L here? Well, the element L there is V plus W. Okay? If I move on, I'm sorry, this should be a Z. In the quadratic group, ignore it. In the quadratic group, the relation becomes, you can subtract the V's. Yeah, so the relation is basically just W. So this guy is mod alpha by W. The relation is W, but the criteria says is D plus W is in the Q span of the relations. There is only one element. There is no Q that you can write B plus W as a linear combination of that. So it is unclear. Okay, I'll pause here. I'll mention something else. Just look at it geometrically. By looking at this picture, I can tell you that this graph is IBM. The reason is, remember that the IBM property says, I'm really interested in, if it's not IBM, then it's going to be, L is going to be some copy of L. One more remark here. Leavitt path algebras are going to be only of, if they are non-IBM, they can only be of non-IBM of type 1n. They cannot be of any type like Fn. This is not possible. And I think either Pereira or Rabea must mention that there is L has a property in the Leavitt path algebras. it's not here. The property of the Leavitt, no, the property of the monoid of non-IBM rings of type Mn is different than the monoid of type Mn. That's why we certainly know the Leavitt path algebras. If they are non-IBM, they can only be of this form. They cannot be of Mn or M greater. Okay, wait for next week, so you might be getting some more results on that. Okay, that's why if the Leavitt path algebra is non-IBM, I'm expecting whatever its type is, it's going to be isomorphic to some copy of that. Well, in terms of the monoid, if I move on to the monoid, what does this mean? This means the sum of the vertices. Well, in our case, what is the sum of the vertices? V plus W. Where is V plus W? It's the point 1, 1. This is the monoid that we see. Well, if I have n times the sum of the vertices, what does that mean? It's somewhere in the diagonal. It's n, if n is 3, it's 3v plus 3w. It is the point, where am I here? 3, 3. That's this. This is 3 times r. This is 2 times the r. This is 4 times r. So, if these are the same, they should be in the same path component. I will be looking at the diagonal then. I will look at 1, 1. If 1, 1 is somehow connected to anything in the diagonal, then I can find that it's not IBM, and moreover, I can tell you what the type is. Well, realize that this is not possible because 1, 1 is in a different component than 2, 2, and a 3, 4, 4, etc. So, by looking at the geometric representation, I can tell you this is going to be IBM. Here's another one. This is non-IBM now. Look at the relation. I have 2 vertices again, V and W here again. So I do the geometric representation. What is the relation? You have 2 relations here. The first one is V. It has 2 loops. So V is equal to 2V plus 2W. And W is equal to W plus V. So I have 1 and 2 relations. I put them in the graph. The red one is the second relation. The blue one is the first relation. V is equal to the point 2, 2. So that's the dark blue one. That's my first relation. I translate it up and right. And I did the same thing with the second relation. This is the sky. I translated up and right. So, well, let's do the algebraic, go back to the theorem. Algebraically it says, if the sum of the vertices, V plus U, W, is in the Q span of the relations. Now, the relations, I go to the relations in the Grothendieck group. So you can subtract. The first relation I get from here is V plus 2W, this guy. And the second relation in the Grothendieck group is V only, W's cancel. And realize that this guy is 1/2 the first relation plus 1/2 the other. It is in the Q span, so L is non-IBM. This is an invariant. Okay, so that tells me the non-IBMness. When I want to know what the type is, for the type I look at the geometric representation. I look at over here, this is the 1, 1. You realize that if you move along the same path component like this, I get to here. And 1, 1 is equal to 3, 3. So R is isomorphic to 3 copies of R. So this is a non-IBM ring of type 1. And it is not going to be isomorphic to 2 because realize that the way that you move is here. this point is going to be moving to the fourth one. If you follow this, just the path components. Okay. So from here as well, R is isomorphic to R3, and R is not isomorphic to R squared is also C. They are not in the same path component. They cannot. Another one. Here I have a Leavitt path algebra with this B and W. The graph I have 3 vertices here, so V is equal to one relation because W is the same. V is equal to 3W plus 2, V is 3V plus 2W. So we have the sum of this element should be in the Q span of the relation. Well, go to the Grothendieck group again, so these cancel. I have the relation to be 2V plus 2W. This guy is in the Q span of the relation. You can multiply this with 1 and L. And so L, the Leavitt path algebra is non-IBM, and it's again of type 1-3. Look over here. The reason I drew them tilted is so that I want to make sure that this is connected with this, but not here. That's why I made them tilted so it's distinguishable. Okay. This one is connected here. This one is connected with the next one, so you can see the path components. And realize that here you have 1, 1. It is going to be connected to 3, 3. And this 2, 2 is not going to be in the same path component. It's totally in another path component. So that gives us the non-idea. Okay, I'll stop here. Thank you.
Remember to send Roosevelt the photos.
Oh, sorry, I erased the email address. Did everybody memorize it by now?
IISER, simple.
Okay, can you hear me? Everything okay? Perfect. Now, everyone, I forgot to give you homework. Okay, I realized that I was extremely tiny. I don't but I'll read it to you. Okay, this is just a slanted view of Leavitt path algebras. This is not a classification. Don't quote me on anything. This is just my little picture that I like to draw. Okay, the left side is the IBM. The right side is the non-IBM. So recall, there are IBM and non-IBM Leavitt path algebras. I think this is very interesting because the motivation for Leavitt path algebras was the Leavitt algebras, which were non-IBM. However, we have a bundle of examples that you can construct. When you get bored at home, or can't sleep tonight or whatever, you can think of constructing examples for each class. The class I have is, I have the Leavitt algebras over here. They're all non-IBM of type 1n. They all sit in the purely infinite simple Leavitt path algebras. Some of which can be non-IBM, some of which can be IBM. They all sit in the family of simple Leavitt path algebras, which can be IBM or non-IBM. They all sit in the family of exchange Leavitt path algebras, which can be IBM or not. And then we have this little tiny set of cone path algebras. Cone path algebras, as Ranga mentioned, they do not have the CK2 condition. However, there is a relation that maybe I should mention. Any cone path algebra is a Leavitt path algebra of a different graph. Oh, actually, I can show it here. In the following manner, cone path algebras, say over K, that's the cone path algebra. Do it in an example. They say more than anything. Actually, we do one vertex only. One vertex, one edge. Say this is our E, our famous E. We like this a lot. The whole path algebra of this graph is isomorphic to the Leavitt path algebra of another graph F. This is a theorem by Pereira, and it is in the famous book that's going to be published. Yes, of Leavitt path algebra. And this is what you do. You double the vertex set that are not sinks. You double all the vertices that are not sinks. Well, I have one vertex which is not a sink. I double it, so I have another V prime. Call the doubling by the primes. Then I look at the edges that start with this regular vertex, and the origin of I'm going to double this edge as well that starts from a regular vertex in the manner that I am going to keep the source of the edge, source of the vertex the same, but the range of the edge will be moving to here. So I double this edge by here. The source is exactly the same, however the range is now, instead of this regular vertex, it's the new vertex. So the Leavitt path algebra of this guy is isomorphic to here, which is nice because this says all whole path algebras are basically Leavitt path algebras. And this is our famous complex algebra. It is proven that whole path algebras are all IBM, that's why I put them here. And believe me, or don't believe me, just check that actually they sit in this set, they cannot be simple. Okay? Well, which is obvious in this picture. Can you describe an ideal? Can you realize that this has a proper ideal? Because it has a sink, right? This is the sink as this is a hereditary, the singleton here generates an ideal, this is a hereditary saturated subset. So it is not simple. So they sit outside. So anyway, when you get bored, you can try to compute examples with two vertex so we can put the graph on, the geometric representation, and check that for everything, whether you can find a non-IBM exchange, non-IBM simple, IBM. I'm here until the end of next week, so I have some examples if you're interested in discussing. Okay, what I want to do to finish off my talks is basically, this is an ongoing research. I'm going to tell you some isomorphism problem on the path algebras. And I'm going to finish off with a normal problem at the end. So if anyone solves the problem, let me know before we go, before I do. Okay, I will need that, but however, let me, actually, wait. This is if you have E, if you consider the graph E in this manner, the way that you define this new F is this form. So if I'm considering the cone path algebra of this graph, it's going to be the Leavitt path algebra of this graph. Just to show you the construction. You have two regular vertices, you double them. U1 to this and this one. And then you look at the edges that end in a regular vertex. This F is not going to be doubled because it ends in a sink. I don't double them. I only double the edges that end in a regular vertex. There is only one, so E will be doubled, and E will start from its regular source, but instead of going to U, it's going to go to its dual. So that's the construction. There is of course an algebraic proof showing that everything nicely matches and there's an isomorphism. and this is in general true. And this is actually true for the more general graphs, the more general path algebras, polynomial path algebras. So anyway, okay. This is something we will use, so maybe I should mention this, and then I'm going to tell you the general problem that we have. For a graph, for graph E0, say you have finite many vertices, we consider the incidence matrix. You might already have known this. Just to remind you, Aij is the number of edges starting with the ith vertex and ending at the jth vertex. So this matrix is going to be the adjacency, the incidence matrix of E. Vi is a sink, then nothing starts with that, so it's a whole row of zeros if Vi is a sink. So just to have a look at the example over here, I say U1, U2, U3, U1, U2, U3. This says there is no vertex from U1 to U1. However, there is one vertex, there's no edge. I'm counting the number of edges. I'm putting the number of edges here. There is no edge from U1 to U1, so that's 0. There is one edge from U1 to U2, so it's this one. No edge from U1 to U3, so this is 0. Again, we're counting the edges, not the paths. There is an edge from U2 to U3, so this is 1. And that's all. We have 2 edges, 2 ones in your instance matrix. Here you have 3 edges. The first one is from 1 to 2, here it is. Then you have 1 to 5, here it is. And then you have 2 to 3, and that's where this is. And I see you have 3 sinks, and you have 3 lines of zeros. So that's the instance matrix. Okay. So this is from another talk that we have already talked about these with you, so I'm going to see it. Let me tell you what the question is. Now, let's say you have 2 rings A and B. You're interested whether whether A and B are, I don't know if there's a standard notation, but I use this for Morita equivalent. If the rings A and B are Morita equivalent, in other words, whether the A modules and the B module are equivalent. Second question, where can I expect, and Professor Agaswamy in the morning mentioned that this is the same thing. If these are Morita equivalent, then their monoids are going to be exactly the same. Another question, are they isomorphic? So I'm asking a stronger one. Third question, are they graded isomorphic? So these are the isomorphism questions that we usually have when we want to classify a certain class or certain structure. Well, this is more stronger than this one. Every graded isomorphic rings are isomorphic. If they are isomorphic, they are Morita equivalent. So you just try to attack the problem. There is still a problem, and it's an open problem. Whether if we take any Leavitt path algebras, under what conditions they are isomorphic, they are graded isomorphic, or they are Morita equivalent. Professor Azad will tell us about the regular isomorphism, so I'll leave that on the side. Again, it is not known under what conditions of the graphs whether these are Morita equivalent, so that's another problem as well. A few things. What do you try to find, or how do you attack such a problem? You try to find some invariance, whether under, I'll talk about this isomorphism problem now. Under the isomorphism of rings, it stays the same. Like some ideals, maybe like Sokal. Sokal is an ideal. If you have if your two rings are isomorphic, their circles will be isomorphic. So that's an invariant ideal. You look at invariance. That's what is that enough? I mean, yes, if I have two rings and I see that their circles are not isomorphic, then I can immediately say, well, sorry, they're not isomorphic. What if the circles are isomorphic? Can you say that the rings are isomorphic? The invariance might not be enough. So I want to find invariance. I want to find enough invariance so that I can immediately say, yes, that's good. I have enough information. Okay. So a few invariants that we're going to look at is this, for instance. If two things are isomorphic, they're Morita equivalent, so this has to be the same. Okay. So some invariants we look at is the V groups. Another one is the K0 groups. When I'm talking, also we mentioned about this guy, the unit order units. I'm not sure which one is the correct name for it. So that's one. This is the non-IBM type. And the order unit are closely related because that's going to have a order in the K0 group, so that will be another one. So if you're looking for this invariant, you should be able to compute it. How am I going to compute it? Smith normal form helps us. Smith normal form is this, just to remind you. If you have a ring of n by n matrices with integer coefficients, for any A, if there exists P and Q invertible in the set, such that this is a diagonal matrix with the entries di dividing di plus 1, this is a unique up to their signs. This diagonal matrix is called the Smith normal form for the matrix set. And the K0 of the Leavitt parallel algebra can be computed by the Smith normal form of this matrix, which is computed by, you take the incidence matrix of your graph, you subtract identity prime, and you get n e prime. And then you find the Smith normal form, and that's going to show. What's I prime? It is the matrix you build from the identity matrix, but you change the columns corresponding to the 6th by column of zeros. And this 1e is exactly what I call L in my model. Okay? That element is seen inside K0, that's the order unit. That's also okay. I'm going to show you how we compute some of the K0s. Just to do an example, I'm going to look at two vertex graphs. So we will have some hands-on exercises to do. That's how I want to finish up today. Now, the isomorphism problem is, before I tell you what the shift move is, okay, it's not known let's say. Take a graph E. I'm going to do this on an example. There is something called a shift move that from this graph E, you produce another graph E. Like how, and it is proved that if you produce a shift move to a graph E and then produce F, then E is being a row finite graph, then the graph of, then the Leavitt path algebra of LKE and LKE are isomorphic. This is known. So at least there exists one move that preserves isomorphisms. Okay? There is another one. I'll just tell you the name. I'm not going to write the moves. There is another one that is known to preserve the isomorphism. That's called the outsplit. I can give you references. I will give. I didn't define what the shift move does. I will in a second. Okay? But there are two moves that you can do to a graph, and that is still preserving the isomorphism. That's all I have, and that's all, as far as I know, is known about preserving the isomorphism. Okay? If you do one move to another, you're certainly sure that the resulting graphs are isomorphic. Okay? Shift move is this. Say I have n loops here, and I'm trying to keep this as simple as possible. F1, maybe I should put enough there. I have, say, two graphs here, two loops here. I'm going to perform a shift move from U to V. The requirement is, first you look at the number of edges emitted from SU. So I'm going to list them. I want to make sure there exists a map. I want one map. From S inverse of U into S inverse of V. Write the number of edges, E1, E2, F1, F2, and then you want to map them to G1, G2, G3, H1, and H2. This map has to preserve, first of all, if you're trying to do this, you have to make sure that the number of edges from in U is less than the number of edges in V. And moreover, when I'm doing this shift move, I have to respect the end at U. So say I mapped E1 to G1, E2 to G2. And also, that's a requirement. I will map, let me write this quickly, F1 and F2, F1 and F2 end at the point B. So you have to map the vertices that are emitted from V, but they have to have their endpoints in V, such that phi of E is the range of phi of E is equal to phi, is equal to the range of E. That has to be also preserved. Once you have such a map, then you can perform the shift move from U to V. What you do is you cancel the edges in V that you mapped. Not the U, you cancel the ones in the V. And then you put an edge from V to U. Each time you perform the shift from U to V, then you put an edge from V to U. One edge. Okay, what happens then? This guy cancel these, and F1 and F2 cancel these. So the shift move produced the graph. Nothing happens to the vertices, not to the edges. Well, nothing happens to the vertices, that's correct. But nothing also happens to the edges here. E1 and E2 stays here. F1 and F2 stays here. We got rid of the loops here, so I have no loops. And I have one G3 here left. But I'm also going to add another edge here. So that gives me 2 plus. So the new graph I have is the Leavitt path algebra on this one is isomorphic to the Leavitt path algebra of the other. Okay. So this is just a tool for that you can play. Okay. Let's move on and then I'll come back. Now, this is an ongoing research. We're trying to classify all Leavitt path algebras with 2 vertex graphs. Any 2 vertex graphs will be of the form. You have U and V, L1, L2, T1 and T2 being the number of arrows there, so just to simplify the notation. So we do this like we have this identifying U with 1, 0, V with 0, 1. This we have already seen in the morning to map this with the homework, the semigroup, the geometry representation. So I'll just skim through some of the results here. We have several different relations that occurs depending on the number of sinks. So if you have 2 sinks, then the graphs is consisting of 2 isolated vertices, correct? Then the Leavitt path algebra you have is basically this. Isomorphic to K cross K. Which is an IBM algebra, we know what this is. If you have a 1 sink, then it's of this form. So this is a sink and there can be some loops here. And there can be some edges emitted over here. So the relation that you have, the semigroup, the monoid, is you have T2 many U's and L2 many V's. And the monoid will be identified by V is equal to this guy, right? It is the relation, so I just modified it, 0, 1. We call the geometric representation is T2, U is your x-axis, V is your y-axis, so it's T2 L2. And if you go to the quadratic group, you can just subtract this one here, so this is what you have, T2 L2 minus 1. Well, recall what the IBN theorem said. If it is non-IBN of type 1m, if 1 minus m is in the integer span of these relations. In other words, you can find a natural number that satisfies this equation. So it turns out to be a linear algebra problem now, nothing else. And if you do the algebra, okay, then the only time that you have a non-IBN solution is this one, where you have some n loops and n minus 1 edges going towards the other side. And the IBN type is also determined. If you have no sinks, then you have this time two relations from the equation. You set up, you have two relations, so you set up in the quadratic group, you have this. And then this is your new linear algebra problem. You have to have, if it's non-IBN, then it's in the linear span of the relations. So you solve this. Now you get different conditions. It's again linear algebra. It's not hard. If this is one, you have another case. You calculate all the linear algebra. It's a good exercise. You can work on it. And then you calculate the non-IBN. There are 4 cases that happens. So by looking at it, and why are they distinct? Because their non-IBN types are different. So I know non-IBN type is another invariant. If they are different, the graphs are, the Leavitt path algebras they produced are going to be different. So I put all of them, all possible non-IBN Leavitt path algebras will be of the following 5 forms. Delta E over here is basically the discriminant of NE that we mentioned. NE was AE minus 1. Okay? And the discriminant of NE is what we call this delta. So, okay. The second one, okay, we have looked at the non-IBN types, that's one invariant. Done. The next invariant is the K0 groups. So we look at this, and we had 5 cases, so we go through each case again. We denote the, I think it's here, yeah, we denote the number of loops. This is the general form. L1, this is U, E1, L2, and T2. Okay. Has this form. So U has L1 loops and T1 edges towards V. This is just to simplify the explanation of the graphs. So we go through. Let me tell you how we compute. Now you look at the AE, the incidence matrix. U does not emit any edges. No, nothing to U, nothing to V, so it's 0, 0. V emits T2 edges to U and T2 plus 1 edges to V. So that's the incidence matrix. But this is a sink. So what is 1 here? It's going to be the identity, but since the first vertex is U is a sink, I replace this column by zeros. This is your identity matrix. And this is 1 prime. The sink, the column of sink is replaced by zeros. And if I subtract this from here, I get the n prime E. I change this to the Smith normal form, diagonalize, and via integer entries. This is the D1 and D2 that you get. So the Grothendieck group here is Z and Z over T2C, which is this guy. Okay, this represents it. So we found the Grothendieck. You do the same computation for every possible graph. You write AE, you subtract it with this guy, sorry, this was the one-sim case, okay? All the others are the no-sim cases. So 1 prime in the other cases are this time exactly the identity. There are no 6 here. So this is 1 prime in this case. So I subtract 1 from here and 1 from here, so I get this as an prime E. The Smith normal form turns out to be this, so you get the case here. You compute it for every other 5 cases, and in each of them you get the corresponding case zero terms. Now, the unit order was embedded in that, and realized that the type in each of them basically is a divisor of one of the K0 groups in each case. That's what has to happen because U is going to be embedded in here. So you put everything in and you see that, oh good, you have the non-IBM types, you have the K0 types, and you can distinguish some of the cases. That these are not going to be isomorphic because the K0 groups are different. Realize that this has the torsion-free part, whereas this is a torsion group. So I know they cannot be isomorphic. See, so these, by playing with the invariants, you try to retrieve some information. We also looked at some other invariant ideals. I'm not going to pass these. This is the Sokal. Professor Mercedes Molina will talk about these next week. The so-called cycle generated by cycles with no exits, and these are this is the ideal generated by the extreme cycles, the vertices on the extreme cycles. So once you compute that, so I'll pass this on, you basically get a bunch of invariants. Now, this is good to point out. Look at the unit order in the IBM Leavitt path algebras is going to be infinite because if R is the ring is IBM, then the K0 has to be infinite group. Then again you do the same thing for the IBMs and you calculate some invariance in the K0s and you get some bunch of other invariants that you look at. So once you look at the table, you can realize this information, these are all invariants, tells you something about the non-isomorphic types. And then you just gather the information. Now, here it is. I'm going to end with this here. There is one case, however, that we don't know the answer. That's how I will add this. This is a graph. This is L2 here. If you start with L1, T1, and L2, there are no edges from B to U. This is the graph you have. Then you can produce a shift move to this one and produce and basically reduce the number of T1s here. By basically you can divide T1 by L2 minus 1, however many times, and you're reducing exactly, okay. I'm doing the shift move, not SU to SD, but SC to SU this time. Okay? So, this is going to stay as it is. What's going to happen is, I'm going to map these edges into here. If T1 is a number number that is greater than L2 minus 1, then basically you have Q Leavitt, where you're leaving division algorithm. So you can put, apply shift move, and each time you can basically get rid of L2 minus you have L2 many here, and then you're going to map it to T1 here. You're going to cancel the T1s, the L2. Correct, yes. Because you're doing the shift move from SV to SU, you're going to cancel L2 many here. However, because you apply the shift move, you have to put an extra edge from V to U. So that tells me that each time I do a shift move, I will reduce this number by L2 minus 1 many edges. I continue doing this until I can. Finally, I won't be able to do it because there is no more L2 minus 1 copies left in the remainder. So you have reduced the number of edges there into L2 minus 1. Well, good. So we need to consider two graphs. And I know that this graph, the Leavitt path algebra of this graph is isomorphic to the Leavitt path algebra of the other one because I applied the shift move. Whether these are isomorphic if I pick different numbers here. Okay, now, this is L2, it's exactly the same, I'm sorry about that. This is L1, L2, and T1 prime. So the only difference is this arrow edge in the middle. The deltas are exactly the same. The reason being, recall from V to U, you have no edge. And in the discriminant, you're going to get L1 minus 1, L2 minus 1. This is T1. And this is T2, but T2 is 0. So it doesn't matter what this guy is here. It's not going to appear. These determine the delta. That's why the deltas in both of them are exactly the same, including the sign. I'll tell you why I'm interested in the sign. Then I look at D. D is the greatest common divisor of the entries in the discriminant. Why am I interested in that? Because that was appearing in the, that is appearing in the K0s, in the K0 groups. That tells me that they're not isomorphic because the K0s are different. Fine. However, if this is the same, the K's and this is different, then K0s are the same, but the types are different. So that is again telling me they're not isomorphic. However, I'm stuck. If I have the case, these are the same and these are the same. IBM type, K0s are the same. Unit order, it doesn't give me any information. It's absolute unknown IBM type. So I don't have enough sufficient invariants to determine whether these are isomorphic or not. I put an open problem as this. This is the smallest example you can build. If you consider the three graphs here, recall this was determining the remainder. So if you have 4 loops here, you will go up till 1, 2, and 3. Those are the 3 graphs that you can reduce them to. The first one produces a non-IBN, type 1, 2. Second and third, they produce non-IBN, they are both of type 1 form. So I know this one are not isomorphic, the last two. However, the K0 groups are, these are Z3, this is type 1 form, and I have no idea whether the the Leavitt path algebras of these graphs isomorphic. Sorry, that's not what I meant. The graphs are not isomorphic, you all know that. Whether the Leavitt path algebras of those graphs are isomorphic or not, I don't know. I'll just say one word because it's known and you might run across to this. These algebras, these graphs, do not produce purely infinite simple Leavitt path algebras. There is a nice classification for the purely infinite simple Leavitt path algebras. It's called the algebraic Phillips. I call it this valid. There, which says this. There's another open problem there, that's why I'm mentioning. Given two graphs, E and F, such that LE and LF are purely infinite simple, if A0 of the first is isomorphic to the K0 of the second, if the this is the Leavitt algebra of this guy is mapped, or rather I should say, the unit order is mapped to the unit order of the other. This is equivalent to saying that the U of this Leavitt path algebra, the U of the yeah, I can say that. U of the Leavitt path algebra is generated by 1, so it has the same order in the K0 group as this one. So you can map this one to the other. The subgroup generated by this one is going to be mapped to the subgroup generated by that. So there's an isomorphism. And 3 is the sign of the determinants are the same. If those 3 are valid, then LE is ring isomorphic to LF. This is known, this is proved by others. However, the thing is that this is the purely infinite simple case. These algebras are not purely infinite simple, so we don't have enough invariants. These 3 things are called the Frank's triple, K0, 1, and the sign of the determinant. The open problem here is this sign really necessary? Okay. Correct me if I'm wrong. In the C-star algebra case, the sign of the determinant is not necessary. You can have still the isomorphism is preserved. However, it's not known whether this is necessary or not to keep this isomorphism. So that is another open problem. Just wanted to mention what is going on in the isomorphism problem. There are a lot of open problems there too. And that's all I have to stop. Thanks for listening.